So the third theory of bonding that we're going to talk about is molecular orbital theory. We are going to do this in a very superficial way because we just need to get some of the ideas from it. So what is molecular orbital theory? This is calculating orbitals for the entire molecule instead of for individual atoms. In valence bond theory, we took the atomic orbitals on the central atom and we hybridized them. And we found that that explained the geometry better than just looking at atomic orbitals overlapping. Here what we're doing is we're taking all of the orbitals from the atoms in a molecule and combining them together into molecular orbitals. So the Schrödinger equation is what describes an orbital, and it's impossible to solve even for a very simple molecule. So the best we can do is approximation. So they take a trial function and they see how that works, and then they tweak it and they try to get to the lowest energy. So they calculate a function that will give the lowest energy. Now this is an approximation of what actually exists in nature. We can never do better than nature at minimizing energy. But the idea is that these orbitals will combine in a way that makes the minimum energy possible. So how do you combine atomic orbitals? Well, we're going to talk about linear combination of atomic orbitals, which is, a lot of words. It's abbreviated LCAO, linear combination of atomic orbitals. This is a weighted linear sum of the valence atomic orbitals for the atoms in a molecule. We're just going to look at the valence orbitals, the valence electrons, not the core electrons. We're assuming those are just going to stay what they are. These are the simplest trial functions that work fairly well. And these are going to combine the valence atomic orbitals of all the atoms in the molecule, not just the two involved in a bond. Valence bond theory just looks at hybrid orbitals, combining orbitals on a single atom. Here we're combining the valence orbitals of all the atoms in the molecule. Many of these linear combinations of atomic orbitals are delocalized over the entire molecule. So instead of an electron density between two atoms, we're thinking of the electron density over the entire molecule. Again, in contrast to the valence bond theory, the hybrid orbitals remained localized on a single atom. So we're going to look at how does this work out, and then we're going to see how molecular orbital theory takes care of some of the things that Lewis and valence bond theory can't handle. So how do you combine atomic orbitals? Well, let's look at the simplest molecule possible, a hydrogen molecule, 2 hydrogen atoms. So each hydrogen atom has 1 electron in the 1s orbital. And so we can combine these 2 orbitals. And again, think about the orbitals as being a standing wave on a string or in ripples in the water, right? And we saw from that video how the ripples overlap and they interfere with each other, right? And they can make constructive interference or destructive interference. So we can add these 2 orbitals together and get a bonding orbital. These are adding these 2 in phase, and what happens then is the energy is lowered. So it's called a sigma orbital because of its shape. There are some things that molecular orbital theory has in common with valence bond theory. It's not a coincidence. It's because they're describing the same sort of thing. So sigma is a spherical or cylindrical type of orbital. If you stood at this end and looked straight down, you would see a circle, right? It's like a little sausage or something. So that's a sigma orbital, and it's called sigma 1s. So here's its name, sigma 1s, because it came from combining 1s orbitals. Okay? It's a bonding orbital because the energy is lower. If it doesn't cause a lower energy, then it's not going to facilitate bonding. Any questions? We can also put these two orbitals together in a way that gives us destructive interference. So you can think of this as adding things that are out of phase, or the way the book approaches it, instead of adding, we're subtracting one from the other. But they're canceling each other out. And so we end up with an orbital that looks like this, where we have one with a positive phase and one with a negative phase. There's two lobes here and a node in the middle. This is higher in energy than the 1s orbitals on each of the atoms. This does not promote bonding. In fact, we call it an anti-bonding orbital. It's against bonding. This is called sigma 1s because, again, it's symmetrical around this internuclear axis, but we give it an asterisk, sigma star, because it's anti-bonding. So sigma 1s is a bonding orbital. It lowers the energy. Sigma star 1s is an anti-bonding orbital. It increases the energy. Any questions? So it's a bit to get your mind around. So adding these two orbitals, we end up with two orbitals. The bonding orbitals lower in energy, and now we see that we've got increased electron density between the atoms. That's going to promote bonding. It's going to cause them to stay together. This is lower in energy. The anti-bonding orbital has a node in the middle, a region of 0 electron density between. This is opposing bonding, this anti-bonding. So we illustrate this in a molecular orbital diagram. And what we have here, I'm waiting for the slide on my iPad to change. Thank you. Energy increasing up, as we always do. We're going to look at the valence orbitals, the valence atomic orbitals for each of the atoms involved. Here's a hydrogen atom. It has one electron in the 1s orbital, so there's a little box. And then over here, the other hydrogen atom, one electron in the 1s box. So this one we've put down because when these combine into the molecular orbital, one of them will flip its spin and they'll spin pair. So the combinations that are possible from these two atomic orbitals, we get two molecular orbitals. One is bonding, it's lower in energy. The other is anti-bonding, it's higher in energy. This comes from adding those two orbitals in phase and adding them out of phase. Or you can think of that as subtracting. Okay, so there's the sigma star 1s and the sigma 1s. Then to do the molecular orbitals, we're going to take the electrons that we have. In this molecule, we have 2 electrons, and we're going to put them into the molecular orbitals that we've drawn, following the same rules that we used for filling up orbitals in quantum mechanics. So these 2 electrons are going into the lowest energy orbital, and they're going to pair up. Any questions? By doing this, the energy is lowered, and that's why hydrogen forms molecules instead of floating around as hydrogen atoms. Because when these guys pair up, their energy is lowered, and so that's more stable. We talk about the bond order. For a diatomic molecule, and we're only going to look at diatomic molecules. For the diatomic molecule, it's the number of electrons in the bonding orbitals, bonding molecular orbitals, minus the number in the anti-bonding. So for hydrogen, the bond order is 2 minus 0, and then it's a diatomic molecule, so we're going to divide by 2, kind of like an average, divided by 2, and so this gives us a bond order of 1. Let's go back to the diagram and look at that. What color do I have going on here? Well, that's fine. So it's the number of electrons in the bonding orbital. So here we have an anti-bonding orbital and a bonding orbital. In the bonding orbital, there are 2 electrons. So we start with 2. And then we're going to subtract the number of electrons in the anti-bonding, because those are going against bonding. There's none there. So we're going to subtract 0, and then we're going to divide by 2. And so this gives us a bond order of 1. That's not too bad, huh? So if that bond order is positive, a chemical bond will form. The higher the bond order, the stronger the bond. Because the higher the bond order, that means the more the energy is lowered by that bond forming. If the bond order is 0, then it's just kind of a neutral situation, bond will not form. If it's negative, a bond will not form, because that would actually increase the energy. You've got more in the anti-bonding orbitals. That makes sense? So bond order greater than 0, the bond will form. The larger the bond order is, the stronger the bond. So if you've got a bond order of 3, that's going to be a stronger bond than if you have a bond order of 1. Okay? Okay, so let's look at He2. An He2 molecule has 2 more electrons. So we draw the diagram like this. Here's the one helium atom, 2 electrons in the 1s. Over here, the other helium atom with 2 electrons in the 1s. And then when 2 1s orbitals combine, we get a bonding orbital and an anti-bonding orbital. Same every time. Now we have a total of 4 electrons to put in here. So we put 2 electrons in down here, and the other 2 go up here. When we calculate the bond order, we have 2 electrons in the bonding orbital minus 2 electrons in the anti-bonding orbital divided by 2, and that equals 0. The 0 bond order tells us this bond is not going to form. And it doesn't. There is no He2 molecule. You can't get it to happen. Any questions? What about an He2 plus ion? That'd be 2 helium atoms making a molecule, and then you've lost 1 electron. So you've got a total of 3 electrons. So we've got this same diagram, but now instead of 2 helium atoms, one of them must have lost an electron. It doesn't matter which one you put on the right side. So here you've got a helium ion and a helium atom. And we're going to combine those 2 together. So now we've got a total of 3 electrons. We'll put 2 down here, and the third one goes up there. So the bond order for this one, how many in the bonding orbitals? 2. How many electrons in anti-bonding orbitals? 1. And then we divide by 2. So that gives us 1/2. That's a positive number. It's greater than 0. So this does exist. Is it common? No, but it does exist. Any questions? So we approximate these molecular orbitals as linear combinations of atomic orbitals. We're taking those atomic orbitals and we're adding them together, or we're subtracting them. This is important. The number of molecular orbitals that are formed is equal to the number of atomic orbitals. If you start with 2 atomic orbitals and combine them, you end up with 2 molecular orbitals. Same thing happened when we hybridized orbitals in valence bond theory. You take an s and 2 p orbitals, and you end up with 3 sp2 orbitals. Orbitals are conserved, you could say. So when we combine 2 atomic orbitals, we make 2 molecular orbitals. One's lower in energy, one's higher. The lower one is the bonding, the higher is the anti-bonding. When we stick the electrons into those molecular orbitals, we follow the same rules. They can hold up to 2 spin-paired electrons. We follow Hund's rule, which is that the electrons are going to take their own orbitals until they have to pair up. So in the quantum hotel, this is, the people are going to take their own beds until they're forced to pair up and sleep upside down. And in order for us to have a stable bond, we have to have a positive bond order. That means that you're going to have more electrons in the bonding orbitals than in the anti-bonding orbitals. So there's our summary. Question?
So in the last slide, that's why the bottom was filled before the top?
Yeah, we fill the bottom before this one, because just like when we were looking at filling individual orbitals when we did like electron configurations, we're going to fill the lower energy ones first. So that's, there are some things here that are the same. Any other questions? We're only doing it with diatomic. Yeah, because that's enough. Yeah. Yeah, it gets really messy if you get 3 or more. Which, people do those, but that's a very specialized area of chemistry that most chemists are like, yeah, I'm really happy that you're doing that because somebody should investigate that, but not interested. Okay, we should be able to do something like this. Use molecular orbital theory to predict the bond order in H2+. Is that bond stronger or weaker than an H2 bond? So how do we do this? Well, we need to draw that little diagram. So we have energy going up, and then over here we have a hydrogen atom, and over here we have, this is H2+, so this one's going to have to be H+. The positive charge means it's missing an electron, so we got to take an electron away from one of these. So we got these two 1s orbitals, and they are going to combine and make 2 molecular orbitals. So one's going to be higher in energy, and one's going to be lower in energy. So this one's going to be sigma star 1s, and this is going to be sigma 1s, because these are 1s orbitals. So these are the atomic orbitals. In the middle we have the molecular orbitals, and this is atomic orbital. So how many electrons does a hydrogen atom have? 1. How many electrons does a hydrogen ion have? None. 0. Right? Because to become H+, it lost its electron. So we've just got the 1 electron to deal with here. So in the molecular orbitals, where are we going to put it? In the lowest energy one. So we'll put it down here. Okay. It's like, well, that's it. That's all it is for this one. What's the bond order? How many electrons in bonding orbitals? 1. How many electrons in anti-bonding orbitals? 0. Divide by 2. So this gives us a bond order of 1/2. The bond order for H2 is 1. So which one is stronger, H2 or H2+? H2 is stronger, right? So this is the answering the question that's given here. This is the bond order for the H2+. Is it stronger or weaker? It's weaker. This bond is weaker because its bond order is smaller than the bond order for H2. Any questions? So that was period 1. We talked about hydrogen and helium. Now we're going to look at period 2. Period 2, homonuclear. Homo is a prefix that means the same, so the same nucleus. So here we're talking about 2 atoms of the same element making a molecule. We will also briefly talk about heteronuclear diatomic molecules. So let's look at lithium. So here's a lithium atom, and here's a lithium atom. We are in the second principal quantum level now for our valence electrons, but lithium only has 1 electron in a 2s orbital, right? So when we combine 2s and 2s, we get a sigma 2s and a sigma star 2s. So again, one is lower, it's bonding, one is higher, it's anti-bonding. Then we take these 2 electrons from the atoms and we put them into the molecular orbitals. And they're going to go into the lowest orbital first and then fill in above as needed. So here they both fit in the bonding orbital. So we could calculate a bond order for this one. How many electrons in bonding orbitals? 2. How many in antibonding? 0. And then divide by 2. So this has a bond order of 1. It's predicted to exist. It does in the gas phase. Questions? We're ignoring the 1s orbitals because those are core. We're only looking at the valence electrons. Okay, Be2. So beryllium has 2 electrons in the 2s. So here's one beryllium atom, here's another one. Again, combining those 2 orbitals, we get an antibonding and a bonding. Now we put the 4 electrons in, 2 of them down here, 2 of them up there. You calculate the bond order. I don't think I need to write it out anymore. The bond order, there's 2 bonding electrons, 2 antibonding electrons. 2 minus 2 is 0, divided by 2 is still 0. Bond order of 0. This doesn't exist. The bond won't form because it's not going to lower the energy. So when we get to boron, now we've got some p orbitals. So we have to look at how do the p orbitals interact. So remember, there are 3 p orbitals, and they are double lobed like this, 1 positive and 1 negative, and they are at right angles to each other. So along the x-axis, the y-axis, and the z-axis, perpendicular. So let's look at just 2 of them, 1 from each atom, and these are along the x-axis. So we can combine these by adding them, and we'll get constructive interference. And so the part between the 2 nuclei gets bigger, or we can subtract them, add them out of phase, and get destructive interference. And now the parts that are on the outsides get bigger, and there's a big old node in the middle where there's no electron density. This is higher in energy. It's an antibonding orbital. Any questions? But then there's 2 other p orbitals, so what do those do? And again, this is sigma because it's symmetrical. If you were to stand at this end and look down, it would be spherical, right? It's symmetrical. Well, the other 2 pairs of orbitals are parallel to each other. And so here we have the py and the py on 2 different atoms. And when these overlap, they're going to add side by side, just like we made the pi bonds in valence bond theory. So we can add these 2 together and get a bonding orbital, which has density here and there, and this density here is between the atoms. Or we can add these out of phase, subtracting them, destructive interference, and we get a big node between the atoms and electron density on either side. This is going to be a star, an antibonding, and this will be a bonding orbital. Now, these are called pi molecular orbitals because they have a different shape. They're not a cylinder. So, no, that's not what I wanted to do. I want to look over here. So when we look at this end-on, right, it looks a lot like, well, you'd see the little red part, and then you'd see the blue part, right, if you're looking end-on. And that kind of looks like the letter sigma. Okay, good question?
Yeah. How do you decide what goes into the antibonding?
How do you decide what goes into the antibonding orbital? Well, right now we're not filling the orbitals, we're just combining them. Okay, so when you're filling them, you fill the lowest energy ones first. And then when that one's full, then you put them in the next higher one, which would be the anti. Yeah. So here, if you look at this one end-on, what's that going to look like? You're going to have this thing over here, and then you're going to have the red thing over here. It's not a circle anymore, is it? So this is the pi. On the next one, it works out better. and I'll show you that. So we could think of it this way. Kind of tip your head to the side. Pi, that helps, letter pi. So a sigma orbital is symmetrical, it's a cylinder, right? And the pi orbital is two side-by-side things like the legs of the letter pi. So the two 2pz orbitals overlapping, they're doing the same thing that the y ones did, but they're just at the right angle to it. So we have two that overlap end to end. Those form a sigma orbital, just like the sigma bonds that we saw in valence bond theory. And the side-to-side adding is a pi orbital, just like the pi bonds we saw in valence bond theory. So the only difference between these orbitals and the others that are formed by the pi p orbitals is the orientation. The energy is the same, just the orientation is different. So how do the pi and sigma 2s and 2p orbitals, how do they rate in terms of energy? It's not always the same, unfortunately. It's determined computationally, and I can't, well, we're just going to learn about it for the diatomic homonuclear molecules. And what we need to remember is that boron, carbon, and nitrogen have a different order than oxygen, fluorine, and neon. And we just know that because somebody figured it out and told us that. The typical energy typical energy ordering for the p orbitals, the sigma 2p and the sigma star 2p are the lowest and the highest. And the pi 2p and pi star 2p are in the middle. So I think of this is normal, this is nice and symmetrical. The sigmas are on the outside, the pi's are on the inside. So this is what's considered typical or expected. We take these 2p orbitals, the atomic orbitals, and we combine them together. We get one that's a sigma overlap, and that's the lowest energy. The sigma star is the highest. And then we have the pi 2p and the pi star 2p. Their energies do not change as much, so they're in the middle. And down here we have the 2s doing its thing. For boron, carbon, and nitrogen, you remember it's those three by saying, be careful now. B for boron, C for carbon, N for nitrogen. Be careful now. The order is different. So what's happened is these two are switched. That's the only thing that's different. So these are switched in order from the ones over here. You always fill from bottom to top. Okay? Now the good news is I'm not going to make you draw these on an exam. I would give you I might give you this and ask you to fill it in. You do need to know that boron, carbon, and nitrogen do it a little differently than the others. Again, be careful now. Why does that happen? It has to do with increased mixing between the 2s and the 2px orbitals. So in boron, carbon, and nitrogen, the sigma star and the sigma are much more separated in energy, and the sigma 2p and the pi 2p are closer. And you know, I really hate trying to explain this. Yeah, I don't like explaining that one. I think it comes up. No, it doesn't come up there. Yeah, so don't worry too much about that. So let's look at all of these guys. Boron, carbon, nitrogen, oxygen, fluorine, and neon. Now what's showing here in this table is just the molecular orbitals, not the individual atomic orbitals. So we look at boron, and each boron atom has 3 valence electrons. So then we have to put 6 electrons into these molecular orbitals. We'll put 2 in this lowest box, and then 2 in that box, and then we've got 2 more, so they're going to each have their own orbital in this next level. We're filling from the bottom to the top, just like we did with molecular quantum mechanics. For carbon, now we're going to have a total of 8 electrons in here, and so they're going to fill up this one. And we add 2 more electrons, and we stick them in here. Over here, these rows have switched in order. Now the sigma 2p is lower in energy than the pi 2p. So let me just go over how these are filling up. So let's just look at neon, Ne2. So each neon atom has 8 valence electrons. So we're going to put a total of 16 electrons into this diagram. And so we start out like this. We put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Do you get the idea?
Why are there more highs here than within the last one? There were only 4 layers, now there's 6 layers. Like I2S, and from that.
Well, on here there's 1, 2, 3, 4, 5, 6.
Okay, all right, so that was all that.
Yeah, what we're looking at is this whole thing in the middle. Yeah. So we can calculate the bond order for each of these guys. So again, it's the number of electrons in the bonding orbitals. So for boron, there's 2 in the bonding orbitals down here, and then these are bonding orbitals. So there's 2 electrons there. So that's a total of 4. Minus 2 in the anti-bonding. So 4 minus 2 is 2. Divided by 2 is 1. So we get a bond order of 1. The bond order for carbon is greater because we have more electrons in bonding orbitals. And for nitrogen, it's even higher because we've got bonding, bonding, bonding. 2, 4, 6, 8. 8 in the bonding orbitals minus 2 in the anti-bonding is 6. Divided by 2 is 3. So the bond order increases. And what we also see is that the bond energy increases. The bond is stronger as the bond order gets larger. And a stronger bond pulls the atoms closer together, so the bond length gets smaller. And so we see that the bond length gets smaller. Okay? Then we get over here to oxygen, and the bond order starts to decrease. So again, we have 2, 4, 6, 8 electrons in bonding orbitals, but now we have 4 in anti-bonding. So 8 minus 4 is 4, divided by 2 is 2. So the bond order decreases. And for fluorine, it's less. And then for neon, the bond order is 0. Neon does not form Ne2 molecules. It just doesn't. Fluorine forms F2 molecules. Oxygen, nitrogen, these guys we're very familiar with, right? Okay, so quick little video here.
When liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid. When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic. Paramagnetic substances have unpaired electrons.
When they say short version, that is a short
When
version.
liquid nitrogen is poured onto a magnet, the magnetic field does not affect the liquid.
So it's pouring through that magnet just like water would. You get a big old strong magnet, you pour water on it, what do you expect? The water's just going to go through, right?
When we pour liquid oxygen onto a magnet, however, it is held by the magnet because oxygen molecules are paramagnetic.
So the oxygen hangs out in that magnetic field. That's weird, right? That shouldn't happen. What's going on? Well, oxygen's paramagnetic. It is attracted to the magnetic field. So we know from that experiment that oxygen is paramagnetic. Paramagnetism is a direct result of there being unpaired electrons. The Lewis model and the valence bond theory model do not explain this. So here's the Lewis structure for oxygen. Do you see any unpaired electrons? No. Looking at that, we would say that oxygen is diamagnetic. It shouldn't be attracted. And here's the valence bond model. And again, we've got the overlap, the side-to-side overlap here, and then we've got our hybrid orbitals. Well, we're not even doing hybrid orbitals there, but end-to-end overlap. But still, we have got no unpaired electrons. You see that? No unpaired electrons. So why does the oxygen stick? Well, when we look at molecular orbital theory, here's the molecular orbital diagram for oxygen. Look what we have here. 2 unpaired electrons. This theory explains why oxygen is paramagnetic. Any questions?
So then the opposite would be diamagnetic.
Yeah. Diamagnetic would be things like liquid nitrogen, which they also poured through there. All of its electrons are paired up, and so it just goes straight through. It's not affected by a magnetic field. So what would happen if you did that with fluorine? Would it stick? No. Are there any of these other ones that would stick? Boron. This is paramagnetic. It's got some unpaired electrons. Okay, draw a molecular orbital energy diagram and determine the bond order for the N2 plus ion. Do we expect the bond to be stronger or weaker than N2? And is this thing diamagnetic or paramagnetic? Okay, let's see if I can do better than I did on Thursday. This takes a little bit of planning. Okay, so we're going to start out with our p orbitals and our s orbitals. So this is a nitrogen atom, and then we've got another nitrogen over here. This one, though, we're going to make that one N plus, because we're doing N2 plus, so one of these has to be missing an electron. Then when we combine these orbitals, so this is 2s, and these are 2p. So we're going to get a sigma 2p and a sigma star 2p. Those come from those guys. When we combine the p orbitals, we're going to get a sigma and a sigma star, and we're going to get pi and pi star. Is this going to be the expected regular order, or is this going to be the other one? The other one. Be careful now. Nitrogen is one of the weird ones. So what we expect is that the sigma would be the lowest and the highest, and that the pi's would be in the middle. That's what we expect. But because this is nitrogen, these two are reversed in order. And you get the idea. Mess, right? This is not, this is a sigma star, 2p. That guy is pi star, 2p. This one is sigma, 2p, and that one is pi, 2p. We need to identify which ones are bonding and which ones are anti-bonding so that we can calculate the bond order. I'm going to do this. I'm going to highlight the bonding orbitals. We're combining a total of 4 orbitals from each atom, and so we should end up with a total of 8 orbitals. We got 1, 2, 3, 4, 5, 6, 7, 8. Half of them are bonding, half of them are anti-bonding. Any questions so far?
Why are the bond to sigma 2p and sigma star 2p should be S?
Yes, those should be S. Thank you. I don't know what I was thinking. Those are S. That's better. Did I screw anything else up?
So the one on the side are...
So these are the atomic orbitals. Just look, that's the kind of the regular stuff that we did a while ago that we were okay with. And the weird stuff we're doing right now in this section is the molecular orbitals in the middle. We're taking the atomic orbitals and we're doing a linear combination of them, and this is the mess we end up with. And we've got energy increasing up. So we're okay with how we drew the diagram? So nitrogen atom, how many valence electrons? 5. So let's put the electrons in here. 1, 2, 3, 4, 5. Right? Over here, this is a nitrogen ion, N+. So that means it's missing an electron and only has 4 electrons. 1, 2, 3, 4. You don't absolutely have to draw the atomic orbitals, but you do need to get the correct number of electrons. So the total number of electrons here is 9 valence electrons. So then we're going to put them in here. We're going to fill from the bottom to the top, low energy to high energy, just like in the quantum hotel. These electrons want to go into the cheaper rooms first. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? What is the bond order? Well, how many electrons are in the bonding orbitals? I made those yellow. 7. So there's 7 in the bonding, and how many in anti-bonding? 2. So that's 5 over 2, or 2.5, right? What was the bond order for the N2 molecule? It's 3. So here's N2. The bond order is 3. The difference between N2 and N2 plus is that one of these electrons is missing. So do we expect this bond to be stronger or weaker? Weaker. Because the bond order is smaller. Is this diamagnetic or paramagnetic? It's paramagnetic. There is one unpaired electron. This is affected by a magnetic field. Any questions? It's some weird voodoo thing, isn't it? It's like learning to play solitaire or something. What about heteronuclear diatomic molecules? So here's the diagram for no. Mo for no. We got a nitrogen atom. Where did that come from? Nitrogen atom and an oxygen atom. So nitrogen has an electron configuration that's 2s2, 2p3, and oxygen is 2s2, 2p4. Oxygen's more electronegative, and so its atomic orbitals are actually a little lower in energy than nitrogen's. And so then when we put these two together, it's a little unbalanced. Right? So these are lower, but these are going to combine. Here, this one, you've got be careful now with a regular one. So what do? Well, I don't expect you to know what to do. But they drew the diagram this way, so we're going to go with that, and we'll say, oh, well, I guess it's regular then. So the sigma's lower than the pi. So you fill those in, and you end up with this molecular orbital diagram. So the high energy atomic orbitals contribute more to the antibonding, and the lower ones contribute more to the bonding orbitals. If we look at something like HF, this is a weird one because fluorine is so electronegative that all of its atomic orbitals are lower in energy than hydrogen's 1s. So here we're looking at fluorine's 2p orbitals. And in fluorine's electron configuration, there's 1s2 and 2s2, and then we get to 2p5. The 1s and the 2s are all lower than the 1s in hydrogen, and even the 2p is lower than the 1s in hydrogen. So how does the 1s overlap with p orbitals? Well, it only overlaps with one of them, and it's going to make a sigma and a sigma star, and then those two are just going to be left doing nothing. They're not really changed. Same energy, but we do get a bonding and an anti-bonding. And so you fill those in. These are they don't contribute to bonding, but they don't oppose it either. They're just neutral. So we've got a bond order would be 1 because we've got 2 bonding electrons and no anti-bonding. So you can imagine how screwy this gets when we go past this stuff, right? So what do you need to be able to do? You need to be able to do diatomic homonuclear molecules. 2 atoms, something from hydrogen up to neon. That's it. Let's do this one. Fluorine and oxygen. We can figure out the bond order. We can figure out whether it's diamagnetic or paramagnetic. The shifts in the orbitals in terms of their energy are not going to really matter for that. If we go back and look at this one, for nitrogen and oxygen, we saw the more electronegative one was lower. Well, thankfully, oxygen is closer to fluorine. They're right next to each other. So we're probably going to end up with a similar situation. Oops, don't know where that came from. Okay. Do you want me to draw the atomic orbitals, or would you be okay with just doing the molecular orbitals in the middle? Molecular orbitals? Yeah. Okay. So for fluorine and oxygen, they've got 2s, and so the 2s are going to make a sigma 2s and a sigma star 2s. And then the 2p orbitals, fluorine and oxygen are both on that regular side. So they're going to make sigma and sigma star, and then 2 pi and 2 pi stars. So the regular order is the sigma 2p, and then we've got 2 here. That's pi 2p. Then we've got pi star 2p and sigma star 2p. It's a lot easier to just draw the molecular orbitals in the middle. How many electrons are we going to be putting in here? How many does a fluorine atom have? Valence. So 7 valence electrons from the fluorine. How many valence electrons does oxygen have? 6. And then the negative charge, do we add or subtract? We need to add an electron. So we're going to have 14 electrons. Okay? So we just fill from the bottom to the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? It wants the bond order. So we've got 2, 4, 6, 8, right, in the bonding, and 2, 4, 6 in the anti-bonding. So that's a bond order of 1. Is it paramagnetic or diamagnetic?
Paramagnetic is when they have
Paramagnetic means they have some unpaired electrons, and diamagnetic means they're all paired up, 2s. It's diamagnetic. Getting those 2 words with the correct concept, I find a bit challenging, because paramagnetic, I want to think they're in pairs, but they're not. Paramagnetic is unpaired. Diamagnetic, the only thing I've come up with is diamagnetic. Di means 2. They're all in 2s. Because this para is not P-A-I-R. It's P-A-R-A, and that has to do with on opposite sides. It doesn't actually have to do with pairing of anything. So if that helps, or if you can come up with a better way, there it is. So it's diamagnetic, and it has a bond order of 1. So we looked at ozone a little bit. Here's a Lewis structure for ozone. We've got resonance. Lewis structure doesn't deal with resonance very well. Valence bond doesn't deal with resonance very well either, actually. So you draw the valence bond model for this, and you end up with this sigma bond here, and a sigma bond and a pi bond here. Neither of these is correct, because experimentally we find that ozone has 2 equivalent bonds. Right? They're 2 like 1.5 bonds. Molecular orbital theory takes care of this. Now this is 3 different atoms, so we're not going to look at how you do the diagram. But you're combining 3 2p orbitals, and those form a delocalized molecular orbital over the entire molecule. So that's how you can have 1 pair of electrons, that extra pair that's neither here nor there, that's actually spread out over the entire molecule. So molecular orbital theory explains resonance. Benzene is a molecule that you'll run into in organic chemistry a lot, and other compounds like it. Here we have, it's called an aromatic ring. It's 6 carbon atoms, and they have alternating double and single bonds in Lewis theory. Well, what's actually true is that they are all 1.5 bonds. The extra pairs of electrons are delocalized. And so what we have is a delocalized molecular orbital that spreads that out over the entire molecule. this sort of resonance causes a great stabilization in the molecule. Benzene is more stable than you would expect it to be. So what do we need to get out of this? We need to have a basic concept of what molecular orbital theory is talking about. And we're just looking at the very, very beginnings of it, looking at the diatomic molecules, just the small ones. Why do we need to study it at all? Because if you're going on to organic chemistry, you need to understand how this can be. And it is the delocalization of electrons over the entire molecule. Any questions?